Hello, to do today we're gonna do some simplification of quantum circuits thanks to ZX calculus. So suppose you have this circuit. The first step will be to transform the circuit into a ZX diagram. So we initialize two qubits in the state 0. We apply Hadamard on the first qubit, and after we apply control NOT gate on the second qubit, control being in the first qubit and the NOT gate on the second one. So how do you transform? So the 0 is like a black point. After the Adamar is a square. Here we transform this into a white gate and this into a black gate. Okay, so yes, normally it's green on the red gates. The fact is, I do not care because it's just a convention, So you can do with other colors if you want. It's easier to do without. So black and white is better than red and green for me. So you have this, and now you just have to show um, if we can remove some gates, or so we can, for example, uh, try to transform this white gate into a black gate because it will give us the possibility to fuse the two black gates. So how to transform a white gate into a black gate? We need to apply Hadamard on each of the branch. So one Hadamard here, one here, one here. And we know that Hadamard is like um, is the identity. So applying both time Hadamard is like doing nothing. So we do this here and here, and this way we'll be able to have one hammer here, here, and here. 1, 2, 2, and so we have 1, 1, 1 as we want. So here we have, yep. Oh, okay, great. After we do this, okay, this, and so we can do this here too. And so yes, we have our three things. So we know that uh, when we have one Hadamard, this this it is equal to a black gate, a black circle. And same in the other sense. Well, I know it's not really great designed. Okay. Oh, you okay? So you just have a circle like that. Like this is a representation of this circle, or this is this. Let's say yes, you have this. Yes. Okay. Okay, that's it. So this gives us the possibility to transform this into a black gate. Yeah, so you remove the three adamers, like the three you want to remove. And so up this. I just remake it for your beautiful eyes. Yeah, that's it. Yeah, we're clearly doing quantum computing now. So, it can be a game. A good way to be good at is to think it as it is a game. So, we're playing right now, my boys. Um, so, as we said, it transforms this into a black gate. And so now we can fuse them because we apply this rule of fusion, saying that if we fuse this and this, it is equal to this. Okay, here we go. I just change this shape. Well, computer is not the best one of the world. Well, fuck you. Uh, my cursor just moved without me wanting him to move. It's really a computer of a computer scientist not working. Okay, yes, so we do not care, we just fuse. So this is a representation of this, and after we just this is just this, and this straight here is this one. So you apply the rule we told you, we have two adamers, so it becomes a wide gate. Okay, and because this is equal to this, like we do not care about it. It's still an identity, you can write it as you want, like left, right, it's ZX. So we have this, but then we clearly can say it's also equal to this, and then we have the cap, which is an important thing in ZX calculus, in the axioms of the language. So we just prove that this circuit can just be reduced to this cap without anything, Yeah, it's like just like just like this. Okay. So what's next? We can have a second example. So let's say you have this circuit. Three control nuts. Well, you can prove that a swap just by thinking of some stilos, like with a real example. Um, I did not work to explain it, but maybe you can try or ask an AI, so you'll be able to do it. So just like this, and you transform it. So into ZX. So black gate becomes white, not becomes this black, not becomes this black. Okay. Okay. So here we have our same. And so you just can apply the up rule, saying 0 that this just we can apply the up rule with more legs, like we have two, so we'll have two connections. But if you have more, you have like three connection extra. So yeah, one black becomes two white, and one black and one white becomes two black, and you link the white and the black. And so the after rule. So you just arrive to this. The advice I can give you is like just draw the rule before. Uh, uh, so this is this, as I told you here. You link them because this is linked to this, like this is linked to this, and we have this one, so write it. And so just like this. So we just get this. We fuse here, we fuse here, we fuse here, we fuse here. And we get this. And so this is linked to this, which is linked to this, so this goes there, and so you have a link between both. And the same here, this goes this, and this go here, so you just have this. And so we have the ideal here, saying there's this. If you just have one input, one output is this, and this too. So the 4 disappears, and you just see that you just have a swap, just the name of this from, which is a common one. And so we just prove, thanks to the Helix calculus, that this circuit has 3 CNETs, it just this. Okay. So I hope it was helpful for you.